I told you only one part of the story. The second part of the story is I call myself a jetophobe. It's too messy, I can't deal with them. Leptons are nice and pristine, I can deal with that, and then my capability stops there. Okay, so today I'll tell you about physics with leptons. In particular, I'd like to actually try and design the experiment, just give you some idea of how we design the experiments. Why is it that it takes so long for us to process the data, come up with answers? There are lots of reasons for that, but I'll go over some of the concrete ones. And then kind of go quickly over the models and all that. I won't spend too much time on that. After all, there are far more capable people here to do that than I am. Okay, so here's a lecture plan. I'll tell you what the search considerations are. I mean, they're not that different from measurements, really, but in particular, because we're all busy looking for new physics, I'll describe how to do a search. Multi-lepton, which is what I do, will be an example. And the key is that it's all about standard model. You can call them fake rates, you can call them whatever, but when you look for new physics, you really can't look for new physics unless you know what's going on with the standard model. So I'm going to make you slog through all these fake rates and all that. And then only will I get to the stuff that you're more familiar with, physics models and results and all that. By the time I'm through slogging through the fake rates, you'll be nodding off, so we'll take a little coffee break. Not real coffee, but Gedanken coffee. So I'll tell you some bad jokes about how to deal with experimentalists. Okay, then I'll get to results and again remind you that beyond standard model is possible only after you deal with the standard model. Some disclaimers. No offense to the jet folks, mono or dilepton folks, but this is, I call it polylepton because one of my students corrected me saying you can't say multilepton because mono and di is Greek, I think, and multi is Latin. Don't mix your Greek and Latin. So he really wants us to call them polyleptons. But anyways, that's what I do. Scott's name will come up quite a bit during this talk because I work very closely with him. It's going to be a CMS-centric talk. And for Atlas, Professor Liplis, who's here, he'll be telling you lots of Atlas things on Wednesday, and Professor Heinemann on Thursday, Friday. She'll in particular will talk about JetMet and backgrounds and things like that as well. I believe she's also going to discuss the future of where we're headed in terms of experimental programs, so I won't be discussing that at all. Please interrupt me with questions anytime. All right. So when we search, we have a very limited capability of what we can do. We have muons, we have electrons, photons. When we dig a little bit into dirt, we get tau leptons, which are a little harder, hadronic taus. Then we have jets. If we have a nice hermetic detector, we're blessed with MET, missing ET, which really is a measure of hermeticity of your detector. And then we derive quantities such as Razor variables, alpha T's, and all that once we have all these basic quantities. So how much money gets spent on the detector has a lot to do with what to expect. For example, photons are wonderful because we have in CMS a wonderful photon calorimeter. CDF, which was my previous experiment, had really lousy muon coverage. And we had to go dig all over to get one muon here, one muon there. And that used to take a lot of time. So it's really a pleasure to work on CMS because thanks to taxpayer money, we have this wonderful detector. So this is typically what you do. You have, let's say, jets plus MET over here. Let's see, how do I point? So here is jets plus MET, no leptons. From here, you can go all the way to 3 or more leptons and throw in a little bit of MET and things like that. That can be E's and mu's and taus. If you have photons, you can do leptons plus photons, and then more than 2 or more photons, all kinds of possibilities. But sometimes you have to keep in mind as your program develops and you're really busy looking at all these things that, there are possibilities such as the new physics may really be long-lived, and so one should always worry about what you're missing as opposed to what you're doing. Okay, I was planning to use Blackboard for this, but maybe it's not not such a good idea. I have the numbers here. So let's begin with various cross sections, and these are the hurdles that stand in the way of getting to new physics. New physics is at the bottom, but let's start at the top. The biggest being W. Because this is a lepton talk, I'll give you cross sections times branching ratios, a TV for E mu tau. So 38 nanobarns, and if I look at our 2012 data, about 20 inverse femtobarns, with 38 nanobarns of cross section just for E mu taus, you get 750 million events. No detector acceptance or anything so far, just how many W leptonic decays were collected, and that gives you two objects. You may say W decays to only one thing, but there is that neutrino, and that neutrino gives you a MET. MET is one of your objects for search. So you have two objects, one lepton and a MET. Next big thing for leptonic searches is Z, on pole or off the pole Z gamma star, gives you L plus L minus. That's 6 nanobarn, 60% of that is on the pole. That 6 nanobarn is over 20 GeV in L plus L minus mass. And that's again of the order 100 million events. Now you again have two objects, namely two leptons. Drelian process typically comes with very small MET, so you don't have any MET. So that's a good handle against that process. Next one, significantly down, but still not negligible, is TT bar. And there you have 24 picobarns to deal with. That's still 500,000 events. That gives you three objects, two leptons and a MET, and the MET. Okay, now in one of the first lectures, Michelangelo talked about reducible and irreducible backgrounds. And I think what I'm showing here is you start with reducible backgrounds, and you're slowly making transition towards irreducible backgrounds. So WZ at the bottom at 1 picobarn level is 20,000 events, and that has all four objects that you would look for in a trilepton search, namely 3 leptons with something else like lots of jet activity or MET or whatever. So you notice that WZ is what you would call irreducible background because you just have to deal with it. It's not something you can just throw out by counting objects. Any questions so far? Okay, so new physics, you can put in whatever number you want. I put in 10 femtobarns. And at 20 inverse femtobarns, that's straightforward multiplication. You have 200 decays to deal with. If you're lucky, the cross-section is 1 picobarn for new physics. Then you got many more, 100 times more. But now it depends on what the new physics, the signature is. If it's 3 leptons, then 3 leptons are kind of livable. As you saw, there's WZ and TT bar and things like that. That'll give you 3 leptons if standard model does something little odd, such as semi-leptonic decays, as we'll get to. But if you have 3 leptons with a little bit of something else, you can live. You can look for new physics. 2 leptons, life is more difficult. So if you need lemonade along with 3 leptons, with 2 leptons, especially opposite sign leptons, you need a stiff drink with that, strong MET, HT or something. If you have to go all the way down to 1 lepton because that's what new physics requires, then you pretty much need something stronger, say sulfuric acid. And now you see why I don't do jets, because then you pretty much need aqua regia or some very strong agent. Because 1 lepton comes with 0 lepton, you have so much background that you're just swamped, and you need a lot more than 10 femtobarn for your cross section. Of course, the flip side is if you're dealing with jets and jet MET searches, then typically your cross section is strong cross section, so the sigma is much higher. Okay. Here's our beautiful CMS detector and schematic. So before you begin designing any experiment, you clearly have to get these objects. Of course, this slice doesn't show it, but it's a hermetic detector, and that gives you MET because that's just what's left over in transverse direction after you accounted for everything else. So here you have magnetic field in there, then there's return magnetic field on the outside, which is why the muon bends as it does. And you collect various objects by looking inside out. First, you do the tracking for all objects of interest except neutrals. So tracking it's done in very strong magnetic fields, so you really know the momentum. Then one by one you collect electrons, photons here, electrons, and then hadronic calorimeter, you pick up hadrons, and then what's left for you is the muon and neutrinos, of course. and the muon goes out, and our middle name is muon, so we really do muon very well. So let's look at our search tools, trilepton search tools, muons, electrons. At a lower peg are the taus. When I say taus, I mean hadronic taus. We'll get into that more. Then there's kinematics, which is where you look at dilepton invariant mass, missing ET, jets, and things like that. Jets, typically you look at number of jets, or you look at the sum of their PTs. And in particular, you also look at BTAC jets. Okay, so now we're in this place where we can design our analysis. So what we do, and this is of course not how I started doing trileptons. When I started on CDF, it was an established search. But now that you have, I had more time on LHC, so when we started that search, we sat down much before the data came and systematically worked out the full hierarchy of what would be the least signal to background and what would be the most signal to background for new physics. Of course, you don't know what the new physics is, so you do all these calculations and estimations based on standard model. Okay, so let's discuss for a second, what is the, with 3 leptons in CMS, what would be the most pristine object? Any guesses? 3 leptons. No guesses? Somebody? Yeah? 3 muons, yes, but what kind?
3 muons all the same sign?
Same sign. Which sign? Which sign?
All of them plus.
Nah, gotcha. No. All of them negative. Because remember, it's a PP machine. So there's higher cross-section for W plus than W minus. And WZ, WZ, W plus Z as opposed to W minus Z. So the most pristine object with 3 leptons would be mu minus, mu minus, mu minus. Then of course would be, mu plus, mu plus, mu plus. Now that I say it, I don't know where E minus, E minus, E minus stands. I believe below mu plus, mu plus, mu plus, because any guesses why? What problem does electron have that muon doesn't in terms of 3 same sign? Charge flip, exactly. There's a significant probability that, non-zero probability that electron will flip sign. So WZ could give you, because of charge flip, it could give you 3 same sign electrons, but getting 3 muons, all negatives, is pretty hard. Okay, so now you get the picture of how we do this. It's done entirely in the context of standard model. I wasn't thinking of what model of new physics will give me 3 same sign muons or something like that. But just based on what the background processes are in standard model, one can play this game. Start with the most pristine state, look at the standard model background, and keep going down more and more into the muck, because as you start fighting more and more for signal and background, more and more for signal, you have no choice but to keep going further down. Okay, so let's keep going. So we exhausted sigma q equals 3, so 3 plus minus 3. So let's get to the next one. So that would be something like, let's just stick to 3 muons. That would be mu plus, mu minus, mu plus. There, we clearly have a problem. As I said, WZ straight gives you mu plus, mu minus, mu plus, so we know that it's not going to be pristine. And if I'm dealing only with muons, I can't even play the game of somehow avoiding Drell-Yan, which is mu plus, mu minus. But if I had mu plus, let's say mu plus and E minus, then I can see that standard model will have harder time getting to that. Anyways, now you understand how we play the game. So here's a summary. So charge Q of plus minus 3, just to let you know, W plus to W minus Z cross-section ratio at AT is something like 80%. It's 1.8. And so you play the games I just mentioned. Then when you get to sigma Q of plus minus 1, there you have mu plus E minus, E plus mu minus, and their charge conjugates. And the reason for that is because there is no opposite sign, same flavor pair in that. So it's harder for standard model to make that. It's called no SSF. Sometimes it's called SSSF. We also call it DY0, Drell-Yan 0 pairs. A question, is there really no Drell-Yan in mu plus E minus? If I just give you mu plus E minus, is Drell-Yan cannot make that? Is that true? Not quite true. Yeah, just one loop standard. Yeah, yeah, z to tau tau would give you that. Because if you have z to tau tau, one tau goes to E plus, other goes to mu minus, you do get E plus mu minus. But it's suppressed because you have the tau branching ratios to E's and mu's at about 30%. So one has to give you, so you can work out the probabilities of getting two dissimilar flavor E's and mu's from z to tau tau. But Drell-Yan does give you SSS, well, SSF or no SSF cases, but it has to go through the taus. The leptons are a bit softer as well then. Okay. So now next hierarchy would be mu plus mu minus mu plus and mu plus mu minus E plus minus. So these are affected by, these are OSSF, they have OSSF pair in them. We call them Drell-Yan 1. In those you have fortunately another handle where there's another hierarchy of the lepton pair invariant mass being more than 90 GeV, you know, not in the Z window, above the Z window, that is more pristine than the one in the Z window, of course depending on what physics you're looking for. And then there is the standard Drell-Yan, which is gamma star below 75 GeV, let's say. Okay, the theory and experiment now diverge, the lingo diverges a little bit. Let's deal with taus now. And to deal with taus, you have to have your Bible. It used to be that you couldn't leave home without it, but with it being online these days, I do leave home without it. But if you look in there, there's a huge dump of information, and I didn't even include all the pages here. So here's a quick relevant summary of PDG. That the tau decays leptonically 1/3 of the time, gives you E's and mu's. That comes automatically for experimentalists. I don't have to do anything about it. Just live with the fact that sometimes, you know, it's not completely in line with the tau. There is a neutrino there. And also that the leptons are softer because, you know, you have to produce neutrinos. Hadronic branching ratios are 2/3. 1/3 of them is single prong. That means it's an isolated track or isolated track with a pi 0, typically. 1/3 of the time, it's 3-prong. That means it's something like, let's say, pi plus, pi minus, pi plus, depending on the tau sign. It's like a pencil jet. At least it doesn't have gazillion particles. It's a narrow cone jet. And for possible future use, it doesn't hurt to remember that if you have a 35 GeV tau, the gamma C tau for tau, I love to futz with first-year graduate students by asking them that question, what's the C tau for tau? Anyway, so that's about 1.7 millimeters. It's not a small quantity. Taus in CMS, quick history. I just mentioned the hadronic branching ratio is 2/3. We use what's called particle flow reconstruction, which means you actually go look at what the decay chain was to some extent and what is the actual identification of the particle. We can reconstruct hadronic taus with about 40% efficiency for PT about 20 GeV. But the bigger problem is that about 1% of jets, and keep in mind there are far more jets than anything else, they still show up as fake taus. And this makes taus a very hard business. It's still useful for some tau-dominated new physics, and let's see what they are. So we'll do that soon, but let's first look at the hierarchy that we wrote down, now including taus. Again, all in the background of standard model. Reminding you that in this table, tau sub h is the hadronic tau. That's an experimental tau. It denotes a reconstructed decay when the parent, namely the theory tau, decays hadronically. Okay, and leptonic decay show for free, as I said. All right, so we have mu plus E minus. These are the Drell-Yan zeros. Then we have mu plus mu minus. These are Drell-Yan 1 pairs with mass hierarchy. And then there is L plus L, so this would be E plus mu plus a hadronic tau. This is called SSOF, though our language gurus always give you trouble. There's no such thing as opposite flavor. Same sign, yes, but there's a different flavor. So at some point, somebody is going to force us to change that to SSDF plus a tau. Then there is same signs, same flavor, so mu plus tau, for example, and so on. And when you get to the more problematic one where you have Drell-Yan plus tau, and remember taus are faked quite a bit, so this is getting to be a problem region. You do the mass subdivisions on Z, off Z, and so on. The very last one we did do in 2011, but this is a very hard one to trigger. So it's nice to reconstruct. You might say, you already reconstruct the hadronic taus, why don't you do this? We get emails from theorists once in a while saying, you did this in 2011, why don't you continue doing it? The reason is the trigger, because the single lepton threshold for triggering have gone up quite a bit, and dilepton triggers is what we really get rest of them out of, but this one doesn't come from dilepton trigger. Once you have all this, now you can do various subsamples in bins of MET, HT, B tags, and so on and so forth. I'm leaving out 4 lepton categories because there's again Z, 1Z, 2Zs, and all kinds of things there that you can play with. Get back to tau for a second. So I give you 3 different examples of where taus are useful and where they're not. And when I say tau, again, I'm talking about experimental tau, hadronic taus. So let's see if we started with 1,000 theory taus. So, and then let's just imagine they have normal PTs met, nothing, the signal, nothing stands out in particular with the signal. So out of that, 33% show up as LLL. By LLL, I mean LL plus E mus, trileptons with E's and mus. And let's say the acceptance efficiency for each lepton is 80%, that cubed is 50%. So 165 survive after reconstruction. And they have reasonable signal to background because you have normal PTs and MET and everything. The other 660 that undergo hadronic tau decay, the news is not very good because the 2 leptons, the E's and mus have to be reconstructed, and then the tau has to be reconstructed with lower efficiency. You get the same number reconstructed as these, but remember, these have much higher backgrounds. So if you just have normal situation and you have a tau, 1 tau in your new physics signal, this is not very useful. That's a marginal increase in acceptance. You keep it, but it's not going to really show up. Okay, now let's get to 1,000 theory taus. But their PTs are high. There's plenty of MET and everything. Now what happens is you get the same numbers again, 165, 165. But because you are kind of swimming in signal to background, even the lousy background that taus have, still you're okay, you can survive, so the acceptance almost doubles if you really have good signal to background to begin with. The third situation where your signal is all taus, high tan beta or whatever, in that case you don't have any recourse, you just throw whatever you got at it, hope for good MET and good luminosity and so on and so forth, and you live with that. Okay, now let's get to the real meat, which is it's all about standard model. So now we get to do the backgrounds. So backgrounds, and there's this standard thing of MC versus data-driven. Patrick earlier had some quibbles with data-driven, but this is a slightly different usage of the term. So the first question to ask is, why not just Monte Carlo out of all the backgrounds, and then you're done. But remember that there's 110 million Z gamma stars, and they give you dileptons, and that many sitting versus 2,000, 5,000 signal events. So that's a huge ratio. And I always like to say devil is in the detail. And when you have 110 million events, they have long tails, and those tails will come and bite you. So that's the real reason why you can't just Monte Carlo. You just cannot do Monte Carlo of something that big. It's like sitting next to some Himalayan peak, and you're at this 6 orders of magnitude below or something, and some snow or rocks are going to fall on your head, even if you really understand the topology of the Himalayas very well. So that's the problem. And it's not academic point because this really happened to the entire Higgs community in 2011. I'll get to that later. So you want to do data-driven backgrounds, and that's where fake rates come in. And the good news here is that because the statistics is so huge, there are large data samples available. When you get to the other end, where your WZ, for example, where it just looks like a trilepton, smaller cross sections means tails peter out, so you don't have to worry as much about tails. You just have to understand the bulk of the background. But you have to validate it quite a bit in various control regions. This is a slide I borrowed from Michelangelo, and this is the buzzword for this lecture, prompt and isolated. So prompt and isolated are the things on which we spend most of our time, because that's what leptons from new physics are. And this is the example that Michelangelo showed, where you have a W, you get a muon and neutrino, that's your met. Nice isolated muon that comes immediately from the W decay. But very similar, you have a neutrino and a muon that comes from, let's say, CC bar. And in that case, what you see is this other stuff around the muon. So this muon may not be isolated. And also, it doesn't come right off of the vertex, but there is some displacement. And that displacement is also something that means it's not prompt, and it may not be isolated. However, we have this 110 million versus few thousand. So even if it's non-prompt, non-isolated, it's going to have tails into prompt and isolated region. Just to look at the number here, there are 100,000 cc bar per W. Okay, so let's first get the simulated backgrounds out of the way. So what we do is for TT bar, we use simulations. But TT bar is kind of in between, and when you use simulations, you can't just say, okay, I simulated TT bar, I'm done. You have to look at it in terms of quantities of interest, in particular here, isolation. So let me quickly define what isolation is. You look at the calorimeter energy around your object of interest in some cone in eta phi. Also look at the track PT and divide it by the object PT. And that's your relative isolation. So I require an isolated muon PT greater than 30 GeV and all that. So this is TT bar data and simulation. And this is what's called single lepton control region, because you have TT bar, you get BW, BW, one of the W decays gives you a lepton. So you look in that sample, but shape that sample so that you really focus in on what you're looking for. This is a little unusual in that normally tails, you look at this side. For relative isolation, your signal is here, so the tails you're looking on are really towards 0. This is where your prompt signal is, prompt and isolated signal, and this is the area where you need to understand, so you make sure that you really understand this plot overall, and that way you don't make many mistakes when you're in this region where there's signal. So you look at require an isolated muon, and this is the other muons in the sample. And again, remember that for B0, the C tau is something like 450 microns, and gamma C tau for 50 GeV B0 is 4,500 microns. This, in here, we're just requiring a large impact parameter of 200 microns, so we know that this is all coming from jets. Any questions at this point? Yeah.
For electron, you have to relax the isolation requirement? Or?
I'm sorry?
For the electron.
Electron, yeah. Very similar isolation. It's similar, yeah. It's pretty much the same, because remember, we have to get the electron out, and there's an algorithm to get the electron out. Once we're done with that, you're probably concerned about all this spray of radiation and all that, but that's all we deal with before we get to isolation. So when we get to defining isolation, we know what belongs to the electron and what doesn't. Otherwise, everybody would be screwing around with that, so that's part of the infrastructure before we start defining isolation. Okay, so that was one lepton control region. Let's go to two lepton control region. Again, because you got two W's in TT bar decay, so you can do the same game now. And here's validation in dilepton control region. You can see that there is HT. HT is the sum of jet PTs. There is the missing transverse energy met. And just to show what I was talking about earlier, although it doesn't matter too much for us, by the time you're getting on the tails, notice that there is some signs of trouble. Okay, so we'll get to met matching later. This is not a problem, but one does have to worry about the tails because TT bar is kind of in between. WZ, completely irreducible. The good news is that the Z has a nice mass and on the Z window, so that lets you tag it. Here is the transverse mass of the W part of the WZ, and what you see here is the data and matched by the Monte Carlo, and in the Monte Carlo you have substantially the WZ Monte Carlo, but of course even ZZ contributes when you don't get the fourth lepton or whatever reason. TT bar has some contribution, and even Drell-Yan, Z gamma star, by picking up another fake, contributes to this mass peak. It's on a log scale, but it's not something that you can ignore when you're looking for new physics. And that's the definition of transverse mass, where you're forming transverse mass of lepton in the met being the proxy for neutrino. Okay, let me get to something which actually does touch a little bit upon future. I just showed you an example of a tail in Met distribution for TT bar, simulated Monte Carlo. So one has to make sure that when you simulate backgrounds, you do match their tails, because in simulation you can get resolutions wrong. So you have to take care of that part, because you can. It's easy to take care of. Long non-Gaussian tails, they're difficult. So let's just discuss the standard good part, the Gaussian part in the middle. And Met being critical in new physics search, that's why one has to really make sure that everything you know about the Met gets thrown at it. Okay, so we must understand, improve its resolution. So we match the Met resolution and data on Monte Carlo in the standard model backgrounds, and learn some interesting things. So I'm just going to show you not our procedure to match data Monte Carlo, but what we learned on the way. So here is Met, X component, and it's for some amount of data, I forget how much, but it's Gaussian to 4 orders of magnitude. For an experimentalist, that's a very impressive plot. Anything that's more than 2, 3 orders of magnitude is just really nice. It's a Gaussian, starts spilling off at this point. It could be just statistics, you can't tell. Maybe just becoming non-Gaussian statistics, or maybe there's some tails. Okay, so I'm not telling you what this plot is, but let's go look at the next plot. It's the same Met X under different conditions. It's only 2 orders of magnitude before it peels off. So what changed? The pristine plot had 10 vertices, so pileup conditions were such that they were low. There were only 10 vertices. HT, the total jet activity, was also low. So let's go back to that plot. So very low jet activity, very low number of vertices, that means low pileup. And what you see from here is that in this plot, it's all n vertices, and HT is on an average 100 GeV. So you see that not only are there tails, but it's also fatter distribution. Okay? So there are 2 different things going on. We increase the pileup, we increase the jet activity, and what we see is that things have gotten fatter and there are more tails. And they're both of concern, so let's try to sort out the 2. So that was the ugly distribution I showed you. And from there, when I require low HT, low jet activity, low pileup, I get nice distribution. Here, I kept the low jet activity, but I increased the number of vertices, that means pileup. And what you notice is that these both don't really have tails, okay? But this is fatter than that. That may seem like a bad thing, but it's not so bad, because this is a stochastic increase. Pileup is stochastic. I just got some random energy while my Met resolution got a little fatter. But remember, new physics is somewhere out here on the tails. I'm far more concerned with tails than I am with the central width, which I can just match in data on Monte Carlo. Okay, so what this tells me is that n vertex, which is pileup, so this is less pileup, more pileup, fatter jets, I can live with, but I can straight away see that random things just make things fatter. The bad news comes, again, same plot, the ugly plot, and now I have all n vertices in both these plots, so pileup conditions are the same. This is low jet activity and high jet activity. And you can see that the tails of the Gaussian come in here. They both have tails in the Gaussian, but this one comes much later than this one. So what this tells me is that higher the jet activity, higher the tails, and this is a bigger concern for new physics. So new physics impact, I can live with fat Gaussians, pileup, but we must make sure that there are no long tails. Any questions on this? There's just something interesting we learned while we're just doing routine data Monte Carlo matching. Okay, so let's get to now the real hard one, which is, let's see, when do I stop? 2:15, at 3, right? It's, no, 2:15, 3:45, right, okay. Not 3, 3 would be bad. Okay, so let's now deal with the real hard one. This is the reducible background, lots and lots of decays, and as I said, you're standing next to the mountain, you better be very careful. All right, so we need very high degree of rejection as well as understanding. So there are dileptons from Z, and a fake lepton give you 3 leptons, so that's the problem. We call them fake, but they're mostly real leptons. They come from semi-leptonics, and these are semi-leptonic decays, so they're neither prompt nor isolated, but there's so many of them that they pose as prompt and isolated. So we do various fake rate methods, and it's a huge industry in my business. And from outside, from theory point of view, it's very difficult to tell who knows what they're talking about. Because everybody has their fake rates. Before you know it, get into long, complicated things, and then you're kind of nodding off. Your eyes are glazing over. But unfortunately, to tell between good experiment and bad, good measurement and bad measurement, you have to kind of learn who does fake rates and all these standard model mundane details in a careful fashion. Anyways, so fake rate methods have to take into account the environment. In particular, remember, it's about prompt and isolated. So if I start playing with isolation and do lots of math and fancy stuff and tell you everything is, I understand isolation completely, but I pay no attention to the prompt part of it, which is the environment where I'm working, then I don't understand my fake rates. And you might have heard a lot about tight-loose methods and all that, and those methods sometimes suffer from looking at isolation. Tight-loose refers to isolation, but not as much to the prompt part. Anyways, in particular, I have to be careful with the B quark or heavy quarks, B and C quark content in the decay products. I'll tell you more what I mean. It should also have good statistical power. There shouldn't be any signal contamination issues that Patrick was talking about earlier. So all those things one has to be careful with. So again, it's a CMS-centric talk, so I'll discuss our own method and show you how it addresses all these pitfalls. Okay, so we want the probability of a third fake isolated E mu in a dilepton sample, and later on we'll deal with the taus, which are harder, but let's deal with E's and mu's first. And the problem is the semi-leptonic B and D decays. So heavy flavor content is very important in wherever you're using these fake rates. So it's not a global fake rate. It's a fake rate that's very specific to where exactly you're looking for new physics. So many leptons with such and such met, so many jets, and such HT, whatever it is that you're looking at, that's where you expect your new physics to be. That's where you need to know in standard model, how many B's and C's are there, how are they decaying, and what are they doing to my fake rate? So I mentioned tight-loose method earlier, so let me not go into that. So what we came up with is a method that addresses both the prompt and isolated issue, and that's what I'll go over. Okay, so I don't want to belabor the issue too much, except to give you an idea that there are some principles involved here, and one has to think them through, but I don't want to go into all the details. The basic point is that you just don't have the statistics when you do this to do something somewhere else and come and apply it to your signal sample. That's one issue. And second issue is that your signal is right in your signal sample. So if you just start counting prompt and isolated objects, you're looking at your potential signal. That's circular logic, so you can't quite do that. So you have to get away from your signal sample. At the same time, use the properties of your signal sample. Otherwise, you might do something that's not appropriate for your signal sample. So here's what we do. We use the non-isolated tracks and leptons in a subsample. So there's a subsample of interest. That's where you're looking for new physics, but either in that subsample, let's say 2 electrons and a muon and met greater than 50 GeV and so many jets or whatever. In that subsample is substantially populated by dileptons, let's say Z gamma star and other things. So that subsample now has a probability of creating a third lepton from semi-leptonic decays. So you want to know what are the properties of this subsample, and what is the probability that a third lepton will be created. So you start measuring global properties of this subsample without counting actual isolated prompt leptons. So you use the non-isolated tracks, and there are plenty of them. And then you also count leptons, not isolated, but leptons, non-isolated, non-prompt. You count all those. And then you say, okay, what is the probability that this track will be isolated? What is the probability that this lepton will be isolated? Okay, and so when you do that, now you're factorizing your quantities of interest. You're not counting isolated prompt leptons, but you're looking at leptons and asking, what's the probability of being isolated? What's the probability of being prompt? And things like that. So here's not to belabor the point too much. So what we want to do is count the number of isolated tracks in the sample and multiply by the known ratio of production rates of isolated muons and isolated tracks. So isolated track is your numerator, and multiplied by the fake rate, in which you have isolated muons divided by isolated tracks as your fake rate. So that's our F mu, probability of an isolated track to be an isolated muon. But again, you got to measure this in the same data set without invoking circular logic. So to do that, you measure the ratio of muons to tracks, and then you say, what is the probability that this muon and track is isolated? So that's the ratio of isolation probability. So you're factorizing your problem. The first factor, it's easy. You just measure it in your subsample. Count the number of muons, count the number of tracks which are not isolated. Take that ratio. The second factor is a global property of your subsample. So it's an isolation efficiency ratio. So you just measure it in your subsample. You're not counting isolated prompt events, leptons, but you're just characterizing the property in this subsample of tracks and leptons being isolated. Okay, but this rate, I just wrote down the same equations again. The second factor, which is measured in the full dilepton data set, but as a function of heavy flavor, so you can use it for your own sub-data set. So this is a global measurement, but it's a parameterized measurement, and you pick as you go through your subsamples. So I have 3 leptons, I have 2 electrons and a muon with MET greater than 50. I have 1 electron, 2 muons with MET more than 75. So I have all these subsamples. If I knew for these subsamples what is the heavy flavor content, then I know what the isolation probability is. And so if I can measure those global properties of the subsets, then I know exactly what I can do for the subset where I'm going to get my new physics. And so this is the answer. I put in these equations just to show you that us poor experimentalists can also do big equations, but there are no F mu nus there, so you're safe. We're not threatening you yet. This is the function that's shown here, and what's shown here is it's a probability of tracks and muons being isolated, the ratio of those two. And what you see is that on this side, and what's on the x-axis here is some quantity, don't worry about what it is, but it's the measure of promptness of the sample. So again, I have some 2 electrons and a muon with MET greater than 50. What is the ratio of prompt objects in it? Prompt objects being Z plus gamma star. If I have Z gamma star, that gives me 2 leptons. That's a very prompt sample. If I have TT bar, there my leptons are coming from B decays, C decays, so that's a very non-prompt sample. So this end is more like TT bar. This end is more like Z gamma star. And so I'm measuring this isolation probability as a function of the promptness of the subsample. So when I use this information for specific search region, my search region could be here, it could be here, it could be here. If I have a B tag in my search region, your new physics requires a B tag, I'm going to be on this side. So I need to know the environment and all of this, and this is on this scale you can see that it varies quite a bit. So when someone asks me, what is the typical fake rate? I could give a number, but it varies widely depending on exactly where you look for new physics. I don't expect you to follow all this, but you can look at the slides later on. It's not that difficult, but I want to give you a flavor that this is not straightforward trivial stuff. Any questions? No? I am making you slog through this, aren't I? Okay. Okay, so let me quickly summarize so we can move on to real physics stuff. So predicting standard model background, so we did all this work. Now let's actually count. How many fake leptons? Again, fake are not always fake. They're non-prompt. They're the tail of non-prompt, non-isolated things that appear as prompt and isolated. Those are my fakes. So I go look at my dilepton sample. I have, let's say, 2 isolated muons. I may have 1 isolated muon, 1 isolated electron, and I have 2 isolated electrons. So those are my dileptons. That's my dilepton sample. And in that sample, I go look at tracks, isolated tracks, and from that I know that I have certain probability of getting 3 muons purely from standard model. I have certain probability of getting 2 muons and 1 electron. The 2 muon, 1 electron can also come from having dilepton sample with muon and electron where I have a fake, where I have an isolated track faking an electron, and so on. So I go through these 3 dilepton subsamples, 2 muons, a muon electron, and 2 electrons, and that gives me probabilities for 3 muons, 2 mu1 electron, 2 e1 muon, and 3 e. And at that point, I'm done with e's and mu's, as long as I remember that for each signal subsample, I had to do this procedure using the properties of that subsample before I can start talking about new physics. Okay? All right. Now let's get to the real problem, which is the taus. Taus are horrible. They just have tremendous, any jets typically would be fat and nice and have lots of particles, but they're going to fluctuate down where you have only 1 or 2 or 3 particles with some pi zeros or photon content, electromagnetic content. You have that and you got a pencil jet with a tau. Okay, so plenty of jets, fake taus. So statistics is not a problem. I don't have to worry too much about statistics, but I do have to worry about the environment. I also don't have to worry about the prompt business here because A, taus themselves are not very prompt, real taus, hadronic decays, and B, my fakes are coming from jets, and the jets, generally, I don't have to go looking for heavy B and C jets. There are going to be plenty of jets from light quarks, so the whole promptness issue goes out of the window, but I do have to worry a lot about isolation. So what you do is, because statistics is not much of a problem, you simply use sidebands. This is my isolated tau. I want to know how many fake tau show up in this region, so I look at the isolation distribution. I look at how many taus are here, call a sideband, and from there I project into the signal region. Extremely straightforward. But as always, there is trouble, because I do some typical isolation shape. But isolation shape is not universal. It also depends on your subsample. So let's look at this. So I just told you, you want to know the fake taus here in the signal region. That's low isolation. Look at the sideband, number in the sideband, multiply by some fake factor, and you got FT, that you got isolated things. But here's the trouble. If you have hard jets in your environment, so you require lots of jet activity because your signal, let's say it's M Sugra type of signal, lots of jet activity. So you demand lots of jet activity, you're going to have lots of jets, in which case your isolation distribution looks like this. It's extremely on the high side. So notice that when I extrapolate from here to here, the extrapolation from here to here is very different from extrapolation from here to here. So just the sidebands is not good enough. I need a little bit more information about the shape. Okay, and this is all theories in a sense. I'm just telling you all these things, but they all have to be verified in data, and I'll show you a plot. But for this hard jet spectrum isolation, this ratio, FT, so ratio of here to here is only 9%, and if it's a soft jet, it's 25%, almost a factor of 3. So you get your, depending on the environment for taus, you could get your background rate off by a factor of 3. Yeah?
What are these axes here?
Okay. Axis is just normalized. It's this arbitrary normalization. So what is the ratio here that I get between here and here? So here is like 9%, just this area versus this area. That's all you're looking at.
What's the
Horizontal axis is isolation. It's isolation distribution. So again, thanks for the question. So let me just explain again what's going on. I have a tau. I define an isolation cone around it. I find the total energy in it. I divide by it. And I say, okay, I have all these tau candidates. I'm going to plot their isolation distribution. What does it look like? And what I find is that I expect it to look something like this. So my tau, energy around it. After all, this fake tau is going to be mostly a pencil jet. So it's a jet, and there is lots of other jet activity around it. So I plot all these things, and I say, okay, here I found an isolated jet, isolated tau, because there is not much jet activity around it. Its isolation is close to 0. This is a very dirty tau because there is huge amount of energy around it. So that's my isolation distribution, huge amount of 7 times the energy that's in the tau itself. So huge quantity of energy around the tau. This is not a fake tau. This is clearly a jet. Part of the jet separated out, looks like a tau. So all the rest of the jet is showing right around the tau, so I can't be faked. But here I can be faked because there is a tau and there's a little bit of stuff going around it, but most of the jet is a narrow jet, shows up as a tau. Okay? But the problem is that when I do these calculations, the shape itself becomes very crucial. And this is the second slide I was showing you, where I have, if I have high jet activity, hard jets, very stiff jets in my sample, then this ratio can be very different compared to when I have very soft jet. That means because it's a soft jet, the energy around my tau is very little. So this is the energy around my tau. This, at this point, is the same as what's in the tau. Here it's twice as much, 3 times as much. So when I get to my isolation window, for a soft jet, I don't have to worry as much. For a hard jet, I get totally different ratio. So what you do is you look at the sideband. So we just account for this entire shape. So we also say, don't just look at this and this. Look at this whole picture. So if you near subsample, in the rest of isolation distribution, you have a lot of stuff. Then use that to make sure that you don't get this part wrong. This is, of course, all highly exaggerated. In real life, it's not that bad. Okay, so all the import of these two, 3 slides is that when you extrapolate from the closed sideband, use the rest of the area as an independent parameter, know it for your subsample where you're looking for new physics, and vary the tau rate accordingly. Here is what we call typical, this is what you have to measure all this in the experiment. All that stuff was just schematic. And here what you see is how much is in the sideband and the rest of the distribution, and what is the actual predicted fake rate. And you can see some variation like that. So more and more stuff there is in the sideband, higher and higher the fake rate, and you can see all that distribution right here. This is the soft jet on this side, this is the hard jet on this side, and you see the variation in fake rate. Okay. All right, so again, now it's getting, your slog is coming close to an end. And so let me deal with the last data-driven background that we have. This background in some other physics searches in CMS and Atlas is done with Monte Carlos, but we prefer to do it with data. So let me begin with a bad joke. How many physicists does it take to forget about Dalitz decays in 20 years? And the reason, and the answer is 6,000, which is CMS and Atlas combined, roughly, or maybe it's 8,000. There's a systematic error on that number. And as Scott likes to call it, it's the only LHC surprise from LHC so far, which is a very sad statement. But so let me tell you what the story here is. So Dalitz decays, it's just not a language used anymore, but if you look at something like a pi 0, very mundane pi 0, I don't even know if any of you remember how pi 0 parity was measured first. Anybody? We do the same thing over and over with different names. It was measured in 1961, I think. Nobody? It's a paper by Plano et al., though I think it was Nick Samuels' thesis. Okay, so, okay, how does one know about Higgs spin? Somebody knows. Come on, just open your mouth, somebody. Which decay mode do you look at? 4 leptons, right? So how do you think pi 0 parity was measured? 4 leptons. So pi 0 to 4e was the decay. Now if you look at the pi 0, and there's always this table, if you look at the pi 0 decays to gamma gamma. But you can also have internal conversion, what used to be called Dalitz decay. So if you look at pi 0 to gamma gamma branching ratio, compare it to pi 0 to EE gamma, where gamma goes internal conversion, that's called a Dalitz decay, or used to be called Dalitz decay. And then if you look at pi 0 to 4e, you can predict the ratios of gamma gamma to EE gamma to EEE in 5 minutes. It's just mostly alpha. Okay, so that we knew very well. And of course, if you did fixed target experiments, you knew all about Dalitz decays, and you looked for them. My student, in fact, wrote a thesis on pi 0 to k0 to 4e, k long to 4e, measuring the CP of the kaon. But we forgot about them, and here's how it came to bite us. So our 2011 data archives, so this is, we're at 70 eV, 5 inverse femtobarn. Here is a plot of observed distribution of data. I should tell you what this is. This is 3 muons, okay, mu plus, mu minus, let's say, whatever, mu plus, mu minus, and another muon. And there's a peak here. After looking at WZ and ZZ and all that, that's vector bosons. Here's a TT bar contribution, very small, and there's a Z gamma star contribution that's very small. We do all that, and we get a nice peak at this 90 GeV. Wonder why that's significant. Because 90 GeV is a Z, a neutral particle, decaying to 3 particles with overall charge 1. This, as you can imagine, was a big surprise. So we saw this, 3 muons, and I deliberately blanked out the main contribution that's giving you 3 muons that peak at the mass of the Z. Okay, and what's going on here is an asymmetric internal, otherwise known as Dalitz photon conversion. So where you have a Z, and from the vertex, not to be confused with external conversion where you have Z to mu mu, let's say mu gives out of a gamma, and the gamma converts to E plus E minus. That gamma doesn't convert to mu or mu plus mu minus or a tau plus tau minus. But when it comes from the vertex, it has no problem creating 2 muons. So essentially what you have is Z to 4 mu. Just as you have pi 0 goes to 4 electrons, from where you measured pi 0 parity, you have Z to 4 mu. One thing that can happen with Z to 4 mu, keeping in mind that Z is, remember, it's 110 million decays. So you have Z to 4 mu. One of these 2 mu's can be very soft. They have wide opening angle. One of them kind of curls out, never makes it out of the detector, and the third one comes out. So you have mu plus, mu minus, and mu plus. And because this was an asymmetric conversion, this guy was soft, this one was soft, you didn't lose much in terms of the invariant mass of the 3 leptons. It really, invariant mass of the 4 leptons and 3 leptons is the same because the fourth one was very soft. And here you have Z gamma star going to LL gamma, which we forgot with the asymmetric conversion. And here we observe a nice Z to 3 mu peak. It's much bigger now with 20 inverse femtobarns at 8 TeV. So it's just part of the routine background calculations. But then we realized, after figuring this out, there was a bit of role reversal between theorists and experimentalists. Scott is the one who I think first noticed this. And I was the one, I think, who later on applied this to WW. So I happened to be on the analysis review committee for WW, standard model measurement. And it suddenly occurred to me one morning as the speaker was headed to a conference that W gamma star and Z gamma star, what's the difference? There's the same problem, the only difference being that when you have W that decays to 1 lepton, this gamma star converts asymmetrically and gives you another lepton, so you get L plus L minus or L plus L plus, equal amount of same sign, opposite sign, but the opposite sign looks exactly like Higgs. And so that was a problem, that was a background that had been forgotten by the community because Dalitz was not in fashion, I guess, anymore. Anyway, so this is a story. What we do is, it's a background for us. We had to deal with it. So what we do is we go to low MET HT region. It's the last fake rate I'm going to tell you about. Measure the ratio of 3 leptons on Z pole to dileptons plus photon that also are on the Z pole. And that's our fake ratio. It turns out to be about 1/3%, specific to what we do. And at this point, I'll ask you for questions, but otherwise, we're done with standard model backgrounds. You can wipe your brows. Questions? Okay. So I have half an hour more, so let's take an intermission before we get to the results. I'll tell you about some peculiarities of how we do things in experimental physics. Now you can look away from your laptops and wake up and all that. Okay, so here's how we waste our time. None of this is, I list the S's, and this S does not stand for smart. So these are the things, these are the bad habits that you guys should, watch out for because it's your job to keep us honest. Patrick was saying that earlier, and I'm going to second him on that, and in fact tell you that Patrick did a very important job of keeping us honest very recently. So let me go through this one by one. Again, there are 6,000 physicists, right, on these collider experiments. But when I write a paper, when you write a paper in the collaboration, what you often notice is this disease has gone down a little bit, but people come back immediately with comments not on your method, not on your fake rates, but on all the missing grammar and wrong grammar and that we call the style comments. So you're hoping that your results would never be wrong because they're going to be vetted by 3,000 very smart people, but if most of them are coming back with missing hyphen and all that, you got a problem. Then there's a second set of community that immediately gets into the statistical method. They skip the whole paper, get to the end. In your conclusion, you use Bayesian, blah, blah, blah. You should have used frequentist, blah, blah, blah. That's the second level of comments. That takes away, another 20% of your energy. Third thing to keep in mind is that we're always working towards the stage. That means it's really gotten to be bad at this stage, so I should mention it. What happens is I have a result, I want to push it through the collaboration. If I put it up, then I get infinite number of questions. I keep going and going and going, and more questions, more answers, more questions, until something magical happens. And that magical thing is there's a conference approaching, a major conference. That removes all kinds of hurdles from my path, because now all the questions, they're not important questions. Let's keep going. If I still have lots of questions, all I have to do is to plant a rumor that Atlas is doing this, it's ahead of us. That takes out some more questions. Now I'm free to go. And so stage is another disease that we have. So again, I should mention, I do take this seriously because we did, for one of the conferences, did push something through. It wasn't vetted as carefully due to combination of two different things. And so we released our result. I won't mention which result because it's personally embarrassing. Though I didn't personally work on it, but I was involved with it. And there was a mistake that Patrick went and noticing. What about this background? How come it's so small? Oops, we missed the biggest background. Didn't affect things too much, but that was embarrassing. Another problem is pseudo-theorists. So there are style people, statistics people, and there are pseudo-theorists. They immediately go into, well, in the doublet model, you should have used this branching versus that branching ratio. Whether your fake rates are right or not, whether your control regions agree or not, I don't care. But in the interpretation, you should go spin more Monte Carlo, do this, that, and other, spend another 6 months. And these people don't worry about the method or the results at all. And that's another problem we have. Citation is, of course, that's a funny S, but it's a S nonetheless, it's citation. Citation is a funny thing because lots of things, and I'll tell you from my career history from a long time ago. I was working on a fixed target experiment, and at that time, light gluinos were very popular. They suddenly became theoretically very important. Somebody realized that the window for light gluino under 10 GeV had not been closed. So I was working on a CP violation experiment, and it turned out that the first night's data was enough to address that issue. So I quickly analyzed that data and wrote a PRL. Back then, it was small enough collaboration that it took me essentially 2 days to write this up. And then, a little bit time after that to push it out, and then it goes in the archives or whatever. And the activity was quite, there were lots of papers coming out on light gluinos, one after other after other. Every day you would open, there'd be something on light gluinos. Then I put the paper out. And that paper got so few citations because the whole industry stopped. So I wrote this wonderful paper, stopped the industry, but no citations at all. The flip side of that, I'm noticing in colliders these days, is that our bosses come and tell us, the other experiment is writing more heavy impact papers. They get more citations. So we should not just write papers, because writing a paper, thanks to style, statistics, and all that stuff, is quite a bit of burden on the collaboration. So let's reduce the number of papers. Let's combine all kinds of things into fewer heavyweight papers, which I call super analysis. And super analysis is where what happens is you combine this mode, that mode, that mode, that mode, and you bring all the guns together out to address one specific physics production, new physics production. Nothing wrong with it, but how you do it is important, because if you do it right, what you would do is you would evaluate the individual pieces critically, make sure they're completely correct, and then you would combine them. What happened in one of our analyses is that we didn't do it that way. We brought all these analyses under one heading, and then when it came to approving this analysis, I noticed that there were no questions whatsoever because everybody who could have asked the question was on the analysis. You're not going to ask questions of your analysis because your colleagues are going to get damn mad at you if you said you could have asked this before. So this analysis kind of went through without much scrutiny, and that's where Patrick noticed and caused us one of the oops. Okay, so that's enough for sociology. You guys ready to get back to physics and models and all that? Okay. Any questions on this? I hope there aren't any. Because if this slide gets through, I am going to get in trouble. Okay, so we discussed all kinds of multi-lepton methods and all that. So let's look at the results. I'm going to speed up at this point. So what we do typically at this point is we don't really pay much attention to what's the signal, where's the signal, what is the background. We just look at all the bins, all kinds of hierarchies, all of them together. They have lots of statistics depending on what standard model does. Some of them don't have any. Those are potentially new signal areas. But sometimes the signal can come into high statistics bins. Whatever it does, it does. So when I look at all these things, so here's an example of this is a MED distribution. And this is not very high statistics, but we understand this is 3 leptons, no Drellian pair in it, so no mu plus mu minuses, no taus, much jet activity, and no B jets. So you have some data, and you can see that there are backgrounds, and the background is dominated. It's hard to see here, but that's TT bar. And above that, at the low MET is, what is it? It's data-driven, that means Drellian and everything else. So we make a number of plots like this. You can see in general the agreement is reasonable, but when you look at so many such things, things do go out of whack once in a while. This one is the same distribution, but we require at least one B-jet. And now you notice that TT bar, which was here but not completely dominant, now suddenly becomes the thing. Because when you require B-jet, remember the prompt versus non-prompt. B-jet means there's a top in that sample, and top is going to be the principal background. So this is what I meant by changing environment for signal regions. So when you change environment from here to here and you do data-driven backgrounds, you better do them differently. Okay. So this is sample result with tau channels. This one is 3 leptons, has a Drellian pair, mu plus mu minus. It's below Z. The moment you have Drellian pair, you get to ask what's the mass of that Drellian pair. This has 1 tau, but no B jets and low hadronic activity. Notice lots of statistics, thousands of events here. And things agree here. This is our data-driven background, then there is TT bar, and then there is WZ, and everything on the log scale. Same thing, except I'm requiring lots of hadronic activity, more than 200 GeV of some PT in jets. Statistics drops quite a bit. Used to be thousands, now it's tens. And also backgrounds flip, TT bar, because I'm requiring lots of HT, TT bar comes with jet activity, so notice the TT bar shot up. So we look at all these plots and make sure that they make sense, that indeed that these colors change as you expect them to depending on what you're doing. If I were to require, there's no B jets here or here, but if I required B jets, the TT bar would completely dominate and things like that. Until you do all this, you're not really ready for new physics, but once you do, this is our summary table, okay? This is not the full result. This is just a summary. This is high HT table for 4 leptons and 3 leptons, and notice that there is counting of Drellian pairs, above Z, below Z, what's the MET, number of taus, number of B jets, this is 0, 0, 1, 0, 0, 1, so on and so forth. So you make huge tables like this, and this is why you have done your background estimations properly. These are your subregions where the environments are different, but new physics could show up. Okay, once you do this, now you're ready for physics, so I'll go over. And any questions at this point before I go into the actual models? And it's a very biased list because this is the kind of thing, these are the things I'm involved with in CMS. What I just showed you in those tables is what we call open search. That's just detailed observations versus expectations. And then you can throw signal at it, throw models at it, see what sticks. Then there is our SUSY, R parity conserving SUSY. There is GMSB derived lepton co-NLSP and tau NLSP models. I'll show you results for that. Electroweak that Patrick discussed in detail. I'll show you results for that as well. Electroweak with or without Higgs is one of the final states. This is natural Higgs, this is strong production. And then one can get to SUSY with R parity violation. There's a host of RPV lambda couplings that we can address with multi-leptons. This also is with and without. These can come with MET, without MET, depending on what these couplings are. There can be third generation, again, based on the couplings. CMS-like simplified models where you have very abstract models which are 100% branching ratios, and the point is that you combine them into some real theory. So a few simplified models, I won't discuss those. Then there is Higgs doublet models, and we also throw in diphotons because whenever there is Higgs, you can always get some mileage by tossing in diphoton along with multi-leptons. So that would be the Higgs or A decaying either to two standard model like Higgs's or Z and a Higgs. Coupling T to C Higgs, there also because you have Higgs and you have a TT bar, other T bar does this normal thing and this one gives you a Higgs, so that again is prone for multi-lepton search. Fourth generation such as B prime or T prime, that also gives you, because you have two of them, you have TW, TW, that's 4 Ws, that gives you multi-leptons. You can also get Z or H out of these depending on what the branching ratio is. In the standard model measurement, you can look at branching ratios, which are our backgrounds for TTW, TTZ. You can also do multiple exotic searches. Tau, because we do taus pretty well, there is something called flavored dark matter. There's seesaw mechanism where you look at the total charge binding. So you look at mu plus mu minus mu plus versus mu plus mu minus mu minus. So net charge plus 1 or minus 1 in seesaw mechanism, that's important. Anyways, this is a very biased list. I didn't mention things like standard model Higgs to ZZ, which also gives you 4 leptons. That's also a very active industry, of course. So let's go to supersymmetry. I'm not going to carry Coles to Newcastle and introduce supersymmetry to you guys. So here is my version of supersymmetry. It's an analogy why we like to double particle spectrum. We used to have electron. Then we decided, well, electron mass blows up, so let's put in a positron. That was 1933 Weisskopf. We come to 2000s, and then now we got this very expensive toy with lots of blades that would be electron, positron, electron, anti-electron, everything. So clearly, this is not quite what Occam's razor means, but this is what we do, and it makes sense. So this is what we look for, and it's too expensive, I guess. And so we throw all these SUSY models at LHC. I cannot take credit for this. This is Stephen Martin, and it's kind of sad to look at that. But and also I should tell you that although at Tevatron we did get to M Sugra with multi-leptons, this is going to be a Sugra-free talk. All right. So SUSY with R parity, let's look into strong production first. Logically, this makes sense. And let me put it to you in historical terms. And actually, the history is going to repeat itself in 2015. So go back to 2010, we felt pretty lonely doing multi-leptons because, as Scott was saying earlier, everybody was doing jets and everything. But Scott himself pointed out that, look, it's not true, because it's not true that all the SUSY is going to show up in jets, because there could be just spectra like this where you have gluinos quarks up there and you get jets, and then down here you get leptons, but these are heavy enough that the real signature comes through leptons, decaying promptly to Goldsteino. So that's this lepton coil. This is GMSP-based lepton coin LSP model. And even in 2010, when everybody was feeling the LHC beam pipe to see if it gets hot with SUSY hadronic production, it's a thermal detector for SUSY. At that time, we did put out this paper. We weren't taking that seriously, because if you looked at the old M Sugra limits and all that Tevatron had, with 35 inverse picobarns, the strong jet met search just blew it off the water. Anyways, because M Sugra had all kinds of complicated things going on, at the Tevatron M Sugra that we ruled out was really due to electroweak production, but this was just strong production with 35 inverse picobarns. Fortunately, after that, people haven't been really talking about M Sugra, although some of the proponents tried to mask it as CMSSM. In our papers, we had to call it CMSSM. We were required to. We couldn't call it M Sugra. But in the very final editing version, I stuck M Sugra back in one of the papers and got away with it. And Atlas never liked that, so they always called it MSUGRA. Anyway, so this is a model, very legitimate model, even with 35 inverse picobarns going beyond the tevatron, no compressed spectrum, etc., and strong production. Something that in this topology, strong searches, QCD searches wouldn't have caught it. So this is now far after 35 inverse picobarns, so we've been making progress on it, and the bounds are pretty strong, things are getting decoupled. So the bounds are approaching a couple of TeV or 1.4 TeV and all that, again because of strong production. I can just give you a hint for SUSY 13, there's another model we're going to put out where this is, again, taking advantage of the tau reconstruction, where taus play a role. It's this tau NLSP model. All I can tell you is keep an eye on it. That's SUSY 13 if we can get it out by then. Okay, after strong production, let's get to weak production. It's not as copious, and as quarks and gluinos get heavier and heavier, it is possible that because they're heavier, weak production might start beating strong production. I'll show you a plot soon. So it's smaller reach in mass because it's less copious, but it's interestingly has less hadronic activity, which is a long ways away from 2010 when we felt rather small because everybody was running after hadronic activity. Now we're at a stage where we're requiring leptons and cutting on hadronic activity of all the places, Large Hadron Collider. And just going back to classic tri-lepton SUSY signature from tevatron, that's where we reached MSUGRA limits. It was a big deal when we did that in CDF, but that was again due to electroweak production. So that's what we're addressing here now, but not in the MSUGRA context. Interestingly, we got quite a bit of grief at CDF for cutting on jets, which we, at that time we were just shooting for MSUGRA, so we said, all right, cut on jets, sensitivity improves, why not? But people said, well, you shouldn't be so much married to a model, that was a mistake. So we learned a mistake, and when we devised this analysis for LHC, we just said we're not going to cut on anything. Everything is all the same, and that's what you saw in the tables. Low hadronic activity, high hadronic activity, low MET, high MET, it's all in there. And if there's no signal, well, it can act as a control region. And if signal is unfortunately there, well, then we got to deal with it. Okay, so what I call the leftward march. So we started with these color production guys. So here is a chart of SUSY cross-section. And here is the number of events, simple multiplication by 20 inverse femtobarns. So if you're at a TeV, for these guys, you still get 100 to 1,000 events. Get to third generation, that number goes down. But if you pick any mass, let's just pick 800, and let's say you ruled out 800 of this, now go across, kind of holding the signal constant. If you go up on 800, go across, come all the way down to the electroweak, you get down to 400. And this is kind of a very rough summary what Patrick was saying earlier, that if you're pushing these higher and higher, then as Scott likes to call it, you have to drain the swamp and start marching leftwards and get as low as you can. Okay, so that's where we are. That's what electroweak production that we're addressing is. These are the various diagrams. So let's just go a step forward. Any questions before I do that? Okay. So these are the electroweakino results that you just saw, some of them from Patrick's talk. I think he had some of the old ones. These are all new from EPS, just as of Friday. So let's look at this model. And in this model, you have democratic decays. It's essentially chargino neutralino. You have 3 leptons. There's some hit you take in branching ratio because of neutrinos. But it's nice democratic decay. And look at our reach. We get to 750 GeV, assuming, making some usual mass assumptions and, factors of 2 here and there in branching ratios that it takes 6 months to deal with Atlas and find out that we're both doing the same thing. Initially, I think we had factor of 2 higher. They didn't. Then they started yelling, cheat, cheat. So we adjusted that. Just normal sociology. And the same model pretty much, but you enrich the taus by having staus here. Just one stau, so you're enriching it, not completely dominating it. And notice, as I said, taus are difficult. What was going to 750 now goes under 700 in terms of limits, just looking at the x-axis. I should have said that this is just the masses of the two neutralinos on the x and y axis. Okay. Now let's go one more step. We had tau enrichment. Now let's go to tau, completely tau domination. So now we have tau here, so we're getting taus all over. When these taus decay to e's and mu's, we do well. When they go hadronically, we get a little bit out. And notice that 700, 650 is now down to 350. And it's not just a game. Nature could be doing this, so that's what we have to live with. On the right-hand side, you see a GMSB ZZ. So here's a diagram. Essentially, you produce two Z's with some MET because of the LSP escaping. And when you have that signature, because you have two Z's, go back to my comment about control regions and signal regions. Typical signal region would be nice, lots of MET, lots of HT, not on Z. Your dilepton pairs are away from Z. But in this one, you're actually producing Z's. So you go back a little bit to your control region. So you're requiring Z's. In case of multi-leptons, you're requiring L plus L minus and L plus L minus, or L prime, L plus and L prime minus. But also comes handy is just the regular Z, dilepton Z, if you can take two more jets, that's not multi-lepton analysis per se, but take two more jets, constrain them to the Z mass. Lots of background still, but you can, they're useful here, both of them, and you can see that you can get a nice exclusion up to something like 350 in this mu parameter, which is like a mass. Okay, let's keep going. Electroweak results. This is now, just as we did ZZ, now that's WZ, charging on neutralinos. Leptons are heavy and decoupled, which is why you get them on, these are on resonance. And now you're down again to 300. There are no taus here. The reason you're down here is because Z is, again, something that used to be your control region. So the signal is somewhat dirty. Okay, but you know, we discovered that particle at 125 GeV. So this is a very incomplete story. Namely, I've been talking only about W's and Z's. But I should be equally well talking about the other boson, namely the Higgs boson. So when you look at electroweak production, it's really required that you also deal with Higgs. So these are internal CMS slides that Scott showed a while ago that I'm just stealing. And the bottom line here is that in the diboson channel, just as we look for WZ, ZZ, we should also be looking for W Higgs, and if it dominates, if it's open. So that's something else that we have to look for. We're looking at it, and not only W Higgs, but even Higgs. And the reason I should mention, I should take you back to the hierarchy that we went through at the beginning of the lecture is, if you keep everything you got, all these channels, low MET, high MET, so many leptons, two leptons, taus and everything, remember Higgs does decay to tau-taus. It's got a significant branching fraction to tau-tau. So although you're dealing with taus, do pay a little bit of bonus. Also having MET, no MET, W's, you know, with so many leptons, 3 leptons, 4 leptons, all that comes handy when you're dealing with Higgs, because Higgs can decay so many ways. Very nice ZZ decay, but dirty W decays because there's no mass, it's just kind of spread out over. The branching fractions you have to deal with, Z it's really bad, W it's reasonable, and tau-tau is also useful. So by the time you throw all that in, a multi-bin approach where you keep everything like a hoarder is really useful. So your signal regions, control regions, you have them all, you throw a signal at it, and the signal will pick whatever it likes. If it's a really high standard model background region, well, you'll get worse limits or you have less sensitivity. Anyway, so that's coming hopefully for SUSY 13. So electroweak summary slide, Patrick also already spent quite a bit of time on this, but you can see this march, leftward march quite well. So this one is the best one, 3 nice leptons, not necessarily on resonance. And this one is another one, so you keep going left. This one, for example, the worst one is chi2, 0, chi1, that's WZ. And that, as I showed you, because it's on resonance, you pay a price. Okay, any questions before I move to the next topic? Okay, let's move to our parity violation. Because although we like, you know, people like to declare SUSY dead, and that, of course, invokes Mark Twain and reports of his death being exaggerated. So same thing here, there are just so many escape valves, it's not funny. Think of R parity violation, your met disappears, or in principle it can disappear. And when it disappears, you know, all those strong searches, jet met searches have a problem that the met disappeared from under them. Also, the even bigger issue that all of us are kind of hiding from, not completely, there are people doing various efforts, but if you look at our tools, MatGraph and all that, you know, how many tools do we have to generate signatures with finite lifetimes? So that's really a nascent field, although there are people doing valiant, you know, efforts and searches in both CMS and Atlas. But it's something that we're just kind of by logic of looking under the lamplight, we're kind of ignoring, and that's something that needs definitely effort. Anyways, R parity violation, depending on the value of the coupling, can have finite lifetimes. And RPV can be tricky, as I said. Don't worry about this slide too much. All it shows is that if you're used to looking for MET, here's a signal, some particular spectrum arrangement, so that you have in leptonic RPV very low MET, okay? And hadronic RPV, you have lots of MET, and things reverse. As you go higher and higher, you're okay, missing ET. So very low MET for hadronic RPV, all your signal is in low MET bin, and leptonic RPV, you're okay. And here is same model, same everything, but if you go to a quantity called ST, where you just throw everything in your calculation, lepton PTs, HT, and MET, then you recover all that signal. So you're binning. I told you already that we do, you know, this and that and mass and so many electrons, muons, taus, we got gazillion bins. Here is another way to bin them. Just MET and HT binning won't do. This signal is beautifully brought out by ST. For this RPV violation, if you just sum all the things, what Atlas calls effective mass, then you get nice signal with lots of ST. But if you were just looking for MET, you would be in trouble for hadronic RPV. Okay, so ST recovers the low MET signal is the bottom line. So here is third generation RPV results. This is what we call natural stop. The reason to put in the word natural is so that you get into PRL, of course. Otherwise, there's no reason to stick necessarily a top in here. But we have all kinds of RPV results, but this is a perfect candidate for PRL. Natural is very fashionable. So here's the stop coming in, giving you a top and a neutral. You know, of course, there's RPV coupling here. You can play with these couplings and get various limits. Notice that because the masses are so high, where limits are, the backgrounds are very low, so you win. At this point, you're just fighting the cross-section and the branching ratio. But you get pretty good limits for stop RPV. That's a 20 inverse femtobond result from a paper that just went to PRL. Another, same paper. Something interesting happens here experimentally, so I want to spend a minute on this. So here we have now a different RPV coupling, everything else the same otherwise. This is LLE233. The 3 tells you there's going to be a tau. And because there is a tau, it's still a leptonic R parity violation. Notice that the limit immediately shrunk. Again, background issues, acceptance and background went from 1,000, 1,100 down to 800, 900. This feature was a bit of a puzzle, cost us a few days to figure out and explain to our collaborators. So let me quickly tell you what happens. There's a sensitivity loss here in the middle because the top goes off shell, just the way masses work out. But what's interesting to note, if you're really used to looking at such plots, and if you're sharp about it, is that here's the expected curve. And notice that the observed curve has a much more of a wiggle than the expected curve. Can anyone guess why? How could that come about? Much, much higher wiggle. So you know, you expect a feature. If you just look at the expected curve, you may not even say there's a feature. Well, something happens, maybe just fluke, we don't know. Maybe your statistics wasn't high enough when you were sampling and thought experiments when you did the limit. But experimental limit is shows clearly that there is a feature there. And the feature we understand kinematically, it's not that important. But what happened here is the result of our multi-bin approach. So what we do is, when you do limits like this, you're generating signal samples everywhere, you're throwing them at your whole gazillion bins, and as you go across, bins are coming in and going out. The most sensitive bins, which will address this signal, are not the same here compared to here. So if you ask me, list all the bins that go into here, classic style of writing paper where you say, We targeted the signal, we looked at this, these are the bins we looked at, this is the signal to background, and this is their answer. Well, it doesn't quite work that way because signal bins are coming and going out, because here maybe the PTs are dropping because of some kinematic feature off shell top. When PTs drop, different control what used to be control channels, lower signal to background channels contribute more, and if they happen to have a fluctuation, then as you go through this region, that fluctuation takes you below the expected. Otherwise, we're doing quote unquote better than expected. So it's a very interesting feature, and such things kind of make your day because it takes a day or two to understand, but it's really what gives you the daily high that you need in order to do this grueling work. Anyways, stop RPV continued. So pause and ask a very important experimental questions. If you look at this limits, their exclusion curves, they're kind of blah, they're just featureless and all that. If you want to get into PRL and good journals, you need something richer than that. So we decided to come up with something more complicated. Now it's so complicated by all we did, let's look at the diagram. It's stop pairs, there is a decay, but the coupling here is LQD233. So it's got hadronic components, and it's got top quark on this side. It's starting with stops, so there's stops here, there's stops in the final state. So you got kinematic features up to wazoo. In fact, we succeeded so well in making it, as you would call it, rich, that I don't have the time to explain it to you in a 90-minute lecture. So here's the result. Again, you see some strange things which are very well understood. So there are all kinds of kinematic regions. If you want, I listed them, you can go look at them. But here is the excluded region, and here's the expected curve, a nice little loop. But notice what the observed curve does. The observed curve is somewhat outside of expected curve, but here there is a decoupling as a function of this y-axis mass, neutrino mass. And so when there's a decoupling, even the slight worsening of sensitivity just blows this off. So there's a huge open area at the top for observed curve because of this decoupling that happens in the cross section, but you expect to exclude very nice region in the center going up to pretty high masses. So all kinds of strange things you encounter. Just for information, I've listed all the regions, what happens kinematically, and it's perfectly well understood. Back to that slide, but I have a rejoinder to Stephen Martin, who made that slide. So that's the SUSY model being eaten up by LHC. But there are many, many non-trivial SUSY scenarios, like the one I showed you, where you have signals with high MET, with low HT. You really don't know what to do, and so you really have to look everywhere because of all these various, for example, here strong production is captured by lepton sector, despite having strong production because it's all accident of the spectrum, something Scott came up with a long time ago. I don't need to spend time on this, but show you this picture, which should come right after this, that there are lots of penguins, and they're reproducing quite well. SUSY is a very amorous theory. It likes, there's no signature it doesn't like. So SUSY isn't going anywhere. So let me end with one topic which is not SUSY. It's B prime, a partner particle. And it again illustrates the versatility of doing this multi-bin approach, the one I showed you in that exclusion where various bins that were different signal to background ratio come in and go out as needed based on what the signal is doing. B prime is very nice because B prime canonical decay is TW, so you get TW, which gives you 4 Ws and 2 Bs. So high mass, lots of Bs, lots of leptons from the 4 Ws. So you can have 3 leptons, 2 leptons, 4 leptons, whatever you want, depending on how extensive you want the search to be. So here's a limit assuming 100%, wait a minute. Here's a limit assuming 100% branching ratio to TW. And it's a pretty nice limit with 9 inverse femtobarns approaching almost 800. Expected curve about 725 or something like that. However, it's a particle that we don't know about really. Maybe it does decay to BZ. So if entirely, let's say the decay is entirely to BZ, then here's a limit again, and now it drops to 660 or something like that. The reason why it dropped is because, again, if you have a Z in the signal, it's competing with Drell-Yan Z, lots of background, so your signal to background is not as good. So you'd pay 100 or GeV or so penalty in the limit or in the search sensitivity. This is a transition plot as a function of branching ratio. So here is entirely BZ. Here is entirely TW, and you can notice that the expected curve gets worse. The observed is a little bit better. The limit is a little bit better. But again, as I told you earlier, as you go from here to here, this is a completely non-resonant signal. TW, 4W is no resonance whatsoever. At this point, you're entirely BZ. You have two resonant Zs. So as you move from here to here, analysis that has multi-bin, so you don't throw out anything, just keep everything. It's making nice progress from one end to another without losing sensitivity. Okay, so I'm at the end of my time, so let me quickly conclude. This is talked to you about CMS multi-leptons. This is an example of a very broad search. And now that we have a couple of years or a year or two before we get new data, although of course we have to get ready for it, we do have to look a little bit harder at the data than we did in 2011. So that's what we're doing, a detailed search, capable of addressing all kinds of strong production, R parity violation, electroweak production, even accidents of spectrum that I showed you where you get low MET, but ST is fine, low HTN, ST is fine, and things like that. MET can be missing in RPV hadronic. There were surprises. The one I didn't mention was when we started in 2010, you might have seen this very pristine ZZ to 4 mu event that came out. It was something actually we saw. In CMS, we were the first one to see that. It made posters all over the world. It looked just like Monte Carlo event. It came in when we had 3 inverse femtobarns, 3 inverse picobarns, and we had no business getting it until about 220 or 300 inverse picobarns. So that event came way too early. That was a big shock to the extent that we thought maybe something strange is going on in the Higgs, because ZZ, of course, is a Higgs channel. We got a very rare 4-lepton event in 2011, huge ST meaning sum of lepton, PT, hadronic activity, and MET. It had B tags, and as far as I could tell, it's very consistent with TT Higgs. This was in 2011 with 140 inverse picobarns, but TT Higgs is still not really ready to be seen. So we still have that event outstanding. And I already mentioned the trimuon Zs, violating apparently charge conservation and its impact on Higgs. So I'll conclude with the credits. Thanks to PITP organizers, my postdoc Richard Gray, Scott Thomas, LHC staff, and so on and so forth. Thank you.